Welcome to my lecture. Today we are going to discuss International Mathematics Olympiad 1959. We'll solve one problem, and the problem is that prove that 2n plus 1 n plus 4 over 14n plus 3 is irreducible for every natural number n. First, we'll recall about some basic requirement for this question. So first is that GCD, greatest common divisor. So the GCD of two numbers, say A and B, is known as greatest common divisor of A and B, and notation used for this is GCD AB. Let's take a few basic examples. GCD of 3 and 7. So 3 is divided by 1 and 7 is divided by 1 and 7 itself. 3 is divided by 1 and 3 itself because they are prime number. So the greatest common divisor is 1. 36 and 54. So if you distinguish the factors of 36 and 54, you'll see that the greatest common divisor is 9. 4 multiply 9 is 36 and 9 multiplies 6 is 54. So we have the greatest common divisor is 9. 48 and 72, the GCD is 24 because 24 multiplied 2 is 48. 24 multiplied 3 is 72. Now what is irreducible? A over B is irreducible if GCD of A and B is 1. So this is the definition of irreducible. This is the definition of irreducible. So we have to basically find the GCD between the numerator and denominator. And for finding the GCD, we have a known algorithm which is known as the Euclidean algorithm. So this is an algorithm to find the GCD AB. So now first question is that if A is equal 0, then GCD of AB is equal B. Why? Because the 0 is divisible by all the number and B is the highest divisible number for B is B itself. So therefore the GCD will be B. Same way, if B is equal 0, then GCD of AB will be A. Now consider the case when both are not equal 0. So in this case, A over B can be written as A is equal B multiply Q plus R. Here Q is the quotient and R is the remainder. Then the Euclidean algorithm says that GCD of AB is equal to GCD of BR. So GCD of B and so if you continue, so you will get a reduced number and then finally you can calculate the GCD when you have a very small number. And repeat the process for B and R until you are getting the answer. So let's start with one example with this. Let's say we have to find that GCD of 250, 195. So we will apply the Euclidean algorithm to find the GCD. So now we can rewrite 250. Maximum number quotient is 1 because 195 multiply 1 and then the remainder will be 250 minus 195 which is 55. So now we have quotient is 1, remainder is 55. So next we need to find the GCD. For that we will take the GCD of 195 and 55. So this is by the Euclidean algorithm. So for that then we will write it 195. The largest quotient is 3 and then the remainder will be 195 minus 165 which is 30. So we continue the process and then we'll calculate the GCD of 55 and 30. We can calculate manually here directly, but we will see that how the Euclidean algorithm is coming. So if you tick directly, you will see that 5 is the largest divisor for common for both these numbers. So therefore GCD will be 5. But if we apply the algorithm again, so we can see that 55 can be written as 30 multiply 1 plus 25. So therefore the next part is we have to calculate the GCD between 30 and 25, which is clearly the 5 is the largest divisor between these two numbers. But again, if you do another step, so 30 can be written as 25 multiply 1 plus 5. This 5 is the answer. Therefore, we are getting the answer is 5. So now we understand that what is the requirement and how we can calculate the GCD using Euclidean algorithm. So now we came back to our problem and we'll solve the problem using the previous concept. So we take it here 14n plus 3 because in the denominator we have 14n plus 3. So this multiply 1 will be 14n plus 3, which is less than 21n plus 4. But if you multiply by 2, then we have 28n plus 6, which is greater than 21n plus 4. So that means the quotient will be 1. So we can write this 21n plus 4 is equal 14n plus 3 multiply 1, and the remainder will be 21n plus 4 minus 14n plus 3. And then, so this is the quotient is 1, and this will be the remainder r. And we simplified it, then you will get it 14n plus 3 multiply 1 plus 7n plus 1. Okay. So now next step by the Euclidean algorithm, we have to calculate the GCD between 14n plus 3 and 7n plus 1. So this is the target here. Next we will calculate this GCD. For that we repeat the process and we got it 7n plus 1 is multiplied 2, which is 14n plus 2 less than 14n plus 3, which is the closed number. So thus the 14n plus 3 can be written as 7n plus 1 multiplied 2, and then the remainder 14n plus 3 minus 14n plus 2. Then you will get 7n plus 1 multiplied 2 and remainder is 1. So therefore the GCD of this number is equal 1. So that means we satisfy the conditions, and by these conditions and by the definition of the irreducible, we have that 21n plus 4 over 14n plus 3 is irreducible for all